Picture two archers. The first has a slightly bent bow. Every arrow flies in a tight cluster, but always the same distance left of center. Consistent and consistently wrong. The second has a perfect bow, but a shaky hand. Arrows scattered all around the center. Two ways to miss the bullseye for two different reasons. Models fail in exactly these two ways. A model can be systematically off, too simple to capture the truth, no matter how much data you give it. That steady offset is bias. Or it can be wildly sensitive, a different answer every time the training data shifts even a little. That jitter is variance. Almost every failure is one of these two, or a mix. And this whole lesson is their tug-of-war, the bias variance trade-off. Here's the picture that makes it click, and it's worth burning into memory. 4 dartboards. The gold dot in the middle of each is the truth, the answer we're trying to hit. Across, from left to right, variance grows. Down the side, bias grows. Every dart is one model, trained on one particular batch of data. Top left is the dream. Low bias, low variance. The darts land in a tight knot right on the bullseye. Every model agrees, and they agree on the truth. This is what we chase. Top right, low bias, high variance. On average, the darts are centered on the truth. No systematic lean, but look how scattered. Retrain on a different sample, and you get a very different answer. On target on average, unreliable every time. Bottom left is the flip side. High bias, low variance. A tight cluster, beautifully consistent, but clearly off to one side. Every model wrong in the same direction. That gap from the cluster to the bullseye is bias made visible. And bottom right is the worst of both, scattered and off-center. So bias is a systematic offset from the truth. Variance is the spread across training sets. Two independent things, and a model can have any combination. Now watch bias and variance in real fits. The trick, instead of one training set, imagine drawing many fresh samples from the same source and fitting the same model on each. Bias and variance are about how those fits behave together. The gold curve is the true relationship. On the left, we fit straight lines. On the right, flexible wiggly curves. Same signal, two complexities. Fit lines to 6 different samples. Look, they barely move. Almost the same line every time. That's low variance. Stable, it doesn't care which sample it got. But every one misses the curve, bending the same wrong way. Stable and wrong together. That's high bias. The model is too rigid to follow the truth. Now the wiggly curves. Each bends to chase its own sample's noise, so they thrash all over the place. A totally different fit every time. That's high variance. But on average, they hug the true curve, not systematically off. That's low bias. Flexibility buys low bias at the price of high variance. Rigidity does the reverse. The trade-off, drawn in curves. Time to make this precise. We assume the world hands us a true function f of x plus random noise epsilon we can never predict. Measurement error, luck, the roll of the dice. The noise averages to 0 with variance sigma squared. Our model produces a prediction y hat, random, since the training data is random. Take the expected squared error at a fixed input, averaged over all training sets and all the noise. Something beautiful happens. It splits cleanly into 3 pieces that simply add. Here it is, the bias variance decomposition, one of the most important equations in the field. Expected error equals bias squared, plus variance, plus irreducible noise. Bias is how far the average prediction sits from the truth. The systematic offset. We square it because that's the form it takes in the error. A too simple model has large bias. Variance is how much the prediction jumps around its own average as the training set changes. The spread of the darts. A too flexible model has large variance. And the last term is the noise variance. randomness baked into the data itself. Here's the hard truth. No model can ever remove it. Even a perfect predictor, zero bias and zero variance, still eats this error. It's the floor, the best you can ever do. So which model do we pick? Everything hinges on one dial: model complexity, polynomial degree, tree depth, number of parameters, how much the model can bend. Watch what bias and variance do as we turn it up. Set up the plot. Complexity along the bottom, growing left to right, error going up the side. Now three curves. Bias squared starts high on the left. A simple model is badly off and falls as the model gains the flexibility to follow the truth. Variance does the opposite. Low on the left, then climbing. The more flexible the model, the more it thrashes with the data, and the noise floor sits flat across the bottom. Same at every complexity, because no amount of modeling touches it. Add all three, and total test error is this U. High on the left, where bias dominates, high on the right, where variance dominates, dipping to a minimum in the middle. The most famous shape in the whole subject. Read it in two regions. Far left, too simple. High bias, both training and test error high. That's underfitting. Far right, too complex. High variance, memorizing noise. That's overfitting. And at the bottom of the U sits the sweet spot. Complex enough to catch the signal, simple enough to ignore the noise. That balance is the goal of the whole craft. Let's put real numbers through it. Say the truth is y equals to x plus noise, with noise variance 1. We judge two models at x equals 3, where the true value f of 3 is 6. Model A is dead simple. It always predicts 5. So its average is 5 and variance is 0. It never budges. Bias is 5 minus 6 minus 1. So bias squared is 1. Total 1 plus 0 plus 1. That's 2. Model B is flexible and unbiased. On average, it nails 6. So bias is 0. But it's jittery. Variance 4. Total 0 plus 4 plus 1, 5. Here's the punchline. Model B has 0 bias, the thing we chase. Yet its error is 5. Double model A is 2. The biased but stable model wins. Killing bias is worthless if variance explodes. One more, to see the U appear straight out of arithmetic. Same noise variance, now 4, 3 models of rising complexity. For each, total error is just bias squared plus variance plus 4. Let's add them up. Model 1 is too simple. Bias squared 9, variance 1. 9 plus 1 plus 4, 14. Bias carries almost all the error. Model 2 is balanced. Bias squared 4, variance 3. 4 plus 3 plus 4, 11. Lower, a little variance traded for a big drop in bias. Model 3 is too complex. Bias squared just 1. But variance shoots to 8. 1 plus 8 plus 4, 13. The error climbs back up. Variance has taken over. 14, then 11, then 13. Down, then back up. The U in 3 numbers. The winner is Model 2, the middle one. Not the simplest, not the most complex. Both extremes cost you more. So how do you move along that U? A few levers, each trading one term for the other. Complexity up, bias down, variance up, slide right. Simpler or a bigger ridge lambda. Bias up, variance down, slide left. More data, variance down, bias unchanged, the one lever that doesn't cost you. And ensembles. Bagging cuts variance, boosting cuts bias. Now your turn, pause and think before I answer. A model gets 2% error on its training data, but 30% error on the test set. Is this a bias problem or a variance problem? The gap between those two numbers is the whole clue. I'll wait. Here's the reasoning. Training error is tiny. The model has power, fitting the training data almost perfectly. So bias is low. But test error is huge. It falls apart on unseen data. That gap, 2% versus 30, is the fingerprint of high variance, overfitting. It memorized the training set, noise, and all. The fix: pull left on the U, simplify, regularize, or add data. Trap 1. High bias is underfitting. Its signature is both training and test error high. Too simple to even fit what it saw. Trap 2. High variance is overfitting. Train low, test high. It's the gap between them, not either number alone, that gives it away. Trap 3. The noise is a hard flow. Chasing zero error is chasing a ghost. No model can drop below the noise in the data. Trap 4. More data mainly cuts variance. It barely touches bias. A straight line on a curved world stays biased no matter how many points you add. And trap 5. Regularization isn't free. A bigger ridge lambda cuts variance by deliberately adding bias. Overdo it, and you underfit. Let's lock it in. The world is a true function plus noise. We can't predict. Expected error splits into three that add: bias squared, variance, and irreducible noise. Bias is a systematic offset from the truth. Variance is the spread across training sets, the bent bow versus the shaky hand. Turn complexity up and bias falls while variance rises. So total error traces AU. And the whole art is landing at the bottom of that U, minimizing bias squared plus variance, given the noise you're stuck with. Hold that picture, and every model you tune has a home.